the square wave is a great example of why you need really, higher bandwidth than you expect in a scope. And that's because the square wave in the frequency domain, in theory, extends forever. So I've set up a little, and here I actually just want to show you about FFTs, but I have a square wave, this 300 kilohertz square wave, and I'm going to switch to the frequency domain. And what I'm expecting here is I'm going to have a spike at the fundamental 300 kilohertz, which is exactly what I see. And I can sort of pull out a bit. And here we're looking at 900 kilohertz. Go back. Here we're looking at 1.5, so 500 plus 1 at the bottom there, 1.5, etc. So this is more or less what we expect. And because I've chosen to I'm using a pretty high sample rate, we get this really nice range. So I'm seeing from 0 to 350 megahertz. So this is a pretty reasonable range I'm looking at. To get this, I'm actually using 1 million points in my FFT, so that's huge. And this is kind of one of the advantages of something like the PicoScope, where you've got this display on the software, because doing this on the smaller devices, more embedded processors or DSP running the regular scopes, I think you're a lot more limited. So the Agilent scopes, I believe, all use 16,000 points, which is pretty good. And this is why I say it's sort of reasonable. So the spikes there's not as small a division, and you're missing some of the detail, but you're still getting the basic idea. So we can see up around 900 kilohertz, we're getting one, etc. But as soon as you go to something like, so the Rigol device all use 2048 according to the datasheet anyway, and there's no detail. There's too few points is the problem. So I no longer know what's going on. If you're stuck with this, the best you can do is you've got to reduce the span of your FFT. So it still can be useful, of course, but you should just be aware that you won't be able to zoom in effectively, because those number of points are going to be split between whatever bandwidth you're choosing to use in your FFT. So here I can use 350 megahertz bandwidth and decide to increase the number of points substantially to give me the resolution I still desire. If you're stuck with a smaller number of points and you have a fairly complex spectrum, then you may be forced to start limiting what area you're looking at. And unfortunately, because this isn't like a real spectrum analyzer, you can't shift your center frequency anywhere. The only thing you can adjust is the sample rate. So you're always starting at 0 and then going up to something. And for this reason, it is really useful having a lot of points in your FFT. Remembering this isn't exactly the same as a spectrum analyzer. And I've got a demo also showing you the when you switch between bits, switching between 8 bits, 12 bits, and so forth. Okay, so let's do a little example with frequency suite. So let's go back to megahertz, and I think these settings are all crazy. Let's sweep up to 10 megahertz, and let's increment by, 10 kilohertz at a time, and let's reduce so you can see in the time domain, let's do this quicker. Okay, so that's a pretty quick sweep. And we can switch over back to the frequency domain. Hopefully you don't have epilepsy or something. And you can see it sweeping here. So another kind of cool thing, again, because it's scope-based, it's a little different from a spectrum analyzer in that it's taking snapshots of the spectrum. It's taking snapshots in the time domain and then converting each snapshot to a frequency. So what's kind of cool is that we have these buffer indexes, so you can actually look back and say, okay, well, how is it progressing over time? And you can see that sweep occurring in the frequency domain. So it's sort of another way that it just gives you a bit more of a view of what's going on. Again, for certain applications, this can be very convenient. So that's a little bit of an overview of some of the FFT details, especially looking at the length of the FFT and why it matters.